Hello everyone, I'm back again, ready to continue the review of modules 3 and 5 for the Math for Teachers 1 final. Let's begin with module 3. So the question is, what divides evenly into 27,840? Well, we'll use the divisibility rules to find out. So, a number is divisible by 2 if the last digit is even or is 0. So we see that our number ends in a 0, so that is a smiley face. The number is divisible by 3 if the sum of the digits are divisible by 3. So 2 plus 7 plus 8 plus 4 plus 0 equals 21. 21 is divisible by 3, which equals 7, so that is a smiley face. If the number is a 4, the last digit is a 4, the last two digits are divisible by 4, so 40 is divisible by 4, which is 10, so that is my face. If a number is divisible by 5, the last digit is a 5 or a 0, and the number that we have ends in a 0, so that's my face. A number is divisible by 6 only if it is also divisible by 2 and 3, and 27,840 is divisible by both 2 and 3, which means it is also divisible by 6. 7, number 7 can be a little tricky. A number is divisible by 7 if you double the last digit, then subtract that number from the other digit. This process can be repeated until the answer is small enough to be recognized as a multiple of 7 or not. So let's figure this out. 2,784 minus 0 is 2,784. 278 minus 8 equals 270. 27 minus 0 equals 27. And 27 is not divisible by 7, so that is a big X. A number is divisible by 8 if the last three digits are divisible by 8. So 840 is divisible by 8. So we get 105, and that is the smiley face. A number is divisible by 9 if the sum of all digits are divisible by 9. This process can be repeated until the answer is small enough to easily recognize as a multiple of 9. So 9 plus 7, 2 plus 7 plus 8 plus 4 plus 0 equals 21, and 21 is not divisible by 9. A number is divisible by 10 if the last digit is a 0, and we've learned at the top that our last digit is a 0, so there's a smiley face. Finding large numbers that are divisible by 11 is a little more complicated. You must alternately add and subtract the digits and get an answer that is either 0 or divisible by 11. So 2 minus 7 plus 8 minus 4 plus 0 equals -1. And -1 is not 0 or divisible by 11, so that is an X. How can the process of nines help in solving this problem? Well, it is sometimes very time-consuming to check your calculations without a calculator. I have a method that is historically referred to as casting out nines, now referred to as process of nines. That will give a good indication of the accuracy of your calculations fairly quickly. Let's examine this process using this example. Beginning with the first number in this problem, we add all the digits together. 8 plus 5 equals 18. Now we remove all the equivalents of 9. 18 divided by 9 equals 2, with a remainder of 0. So we can throw out this entire number. Next, we have 6 plus 8 plus 8 plus 8 equals 30. 30 divided by 9 equals 3 remainder of 3. We can throw out the 3 nines, but hold on to the remainder of 3. Now we will look at 2,525. Let's add 2 plus 5 plus 2 plus 5. You can easily see that 2 plus 5 plus 2 equals 9. We can get rid of that first, which leaves only a 5. Finally, the last number in our problem is 6,029. We start by casting out the 9 and then add 6 plus 2, which equals 8. Now we add all of our remainders together, casting out all the 9s again. 8 plus 5 plus 3 plus 0 equals 16. Divide that by 9, and our remainder is 1. And our answer is 1 remainder of 7. Our final indication answer for our problem is 7. Now let's move to the sum that has been calculated. The answer we have recorded is 23,992. The first thing we will do is cast out the 9s. Now we have to add 2 plus 3 plus 2, which equals 7. Since our answer from the problem and the sum are the same, it is very probable that the answer is correct. However, if you accidentally transpose 2 of the numbers or had the same digits in a different order, then obviously your answers would not be correct. That is why I remind you that this process of 9s is only an indication that you probably have the correct answer. How can you use the rods to help solve for GCD, or greatest common divisor? Well, sometimes a picture is worth 1,000 words. My brain often uses pictures to help me remember difficult concepts. When we start using too many acronyms such as GCD, GCF, LCM, and so on, it is easy to get confused, like me sometimes. By the way, GCF, or greatest common factor, is just another name for greatest common divisor. Let's picture the use of rods that are equivalent to numbers 1 through 10. We are going to compare 2 trains of rods, a train of 12 and a train of 15. Next, we line up all the rods that will evenly measure each train. We see that the 12 train can be evenly measured by 1s, 2s, 3s, 4s, and 6s. The 15 train can be evenly measured by the 1s, 3s, and 5s. The longest rod that evenly measures both the 12 train and the 15 train is the 3 rod. It takes 4 of the 3 rod to measure the 12 train and 5 of the 3 rod to measure the 15 train. So the greatest common divisor is 3. I hope this illustration helps you to see how to solve a problem for the greatest common divisor. How can I create a magic square? Of course, everything in math has a logical pattern or algorithm. What may seem random at first always has a reason behind it. We have seen this to be true many times this semester. So let's create a magic square that has the same sum in every column, row, and 3 numbered diagonal. So our first step is choose a sequence of numbers that will provide a number for each box in your square of odd boxes. We will use -3, -2, -1, all the way to +5. Step 2, picture in your mind that the square wraps around from top to bottom and side to side. Step 3, place the first number of your sequence in the top row, middle box. In step 4, follow this algorithm. Sequentially add numbers diagonally up and to the right when you can. Remember the wraparound picture. Move to box below when you can't. Here we go. -3 goes into the top middle box. Now we move up and to the right for -2. But that box is actually at the bottom because this square wraps around, remember? Next, we move up and to the right for -1. But that square is on the other side because of the wraparound from side to side. Next, we add 0 up and to the right. Uh-oh, can't go there, so we put 0 below -1. Then we move up and to the right for 1, and then 2. Since we cannot move up and to the right for number 3, we put 3 directly below number 2. Now, using our wraparound picture, we go up and to the right to all the way around to the opposite side for number 4. Then again, going up and to the right, wrapped around to the bottom or number 5. Let's check our work to see how we did. So the top row is check, middle row check, bottom row check, left column check, middle column check, right column check, diagonal check, and diagonal check. Everything adds up correctly, and this algorithm will work for any square with an odd number of boxes. Moving on to our final module, module 5. How do you change decimals to fractions in lowest terms showing denominators with prime factorization? Yes, this may sound complicated, but if we follow these simple steps, it will seem quite easy. First, we need to realize that every decimal reads like a fraction. Our first number is 225 thousandths, which is equal to 225 over 1,000. We can easily see that both 225 and 1,000 are divisible by 5. After reducing our fraction to 45 over 200, we can see that both the numerator and the denominator are divisible by 5 again. 9 over 40 is the lowest term for this fraction. Now let's look at 36 thousandths. It is equal to 36 over 1,000, which are both even numbers divisible by 2. We can divide the numerator and denominator by 2 and reduce the fraction to 18 over 500. Again, we can reduce this fraction by dividing each part by 2. Now we have 9 over 250, which is lowest terms for this fraction. Next, we will look at showing the denominators using prime factorization to make this illustration easier to read. The prime numbers that divide evenly, that divide both, is purple. If it only divides into the 40 side, it will be red, and if it only divides into the 250 side, it will be blue. After factoring out both numbers, we have 40 equals 2 times 2 times 2 times 5, and 250 is 2 times 5 times 5 times 5. In order to present this information correctly, we have 40 equals 2 to the third power times 5 to the first power, and 250 equals 2 to the first power times 5 to the third power. How do you find the fraction and the percent of the red shaded portion? Well, when you're looking for a fraction and a percent of a shape, the first thing we must do is make sure all the parts are the same size. Let's begin with a simple example. There are 2 parts of equal size and 1 part is shaded. Our fraction is 1/2, which is 1 divided by 2, which is 0.5, which is 50%, or 50 out of 100. Moving on to our problem, you can see there are 9 squares within a square. 3.5 squares are red, but we cannot make a fraction with a numerator of 3.5. So notice how we divided all the squares into triangles. Now there are 18 parts, the denominator, and with 7 of the parts shaded red, 7 will be the numerator. Evenly, every fraction is a division problem. We get 0.3888, which is about 39%. We just rounded up to the nearest hundredths place for the percent. So in order to find the fraction, the number of shaded portions is the numerator and the number of total portions is the denominator. It is very important to be sure that all portions are equal in size. To find the percentage, remember that every fraction is a division problem. Divide the numerator by the denominator. Percent means out of 100. So we get the percentage by moving the decimal point to the right of the hundredths place and adding a percent sign. Next question is, how can I determine approximate percentages of the whole? Well, the whole in this activity will be the hexagon. We will compare the shapes below to the whole to determine which shape is the smallest percentage up through the shape that is the largest percentage of the whole hexagon. To begin, I've listed all percentages from least to greatest. So which shape appears to be the smallest and therefore be 16.67% of the whole? Let's see. I think it would be the triangle, the green triangle at 16.67%. The next one is the tan trapezoid. My bad, not trapezoid, it's a rhombus at 19.2. The third one would be the blue rhombus at 33.3. And the fourth one would be the red square at 38.5. And the last one would be the red trapezoid at 50%. So I can see that I can fit about 3 green triangles in the first one. So I would multiply, 6, my bad, 6. Be 16.67 times 6 to get 100%. I can see that I can fit about 3 blue trapezoids, rhombus, in the third one at 33.3 times 3 to get 100. And I can fit about 2 trapezoids into the last one, so 50 times 2 is 100. So for the shapes that do not have an easily divisible percentage or an obviously whole number fit into the whole, we simply look at each shape's relative size compared to the rest of the shapes to determine the percentage. For our last question, how can you complete the 3 common types of percentage problems? Let's use a real-life example to help you understand 3 common types of percentage problems. I want to make a smoothie for 3 people. It takes 1 cup of almond milk for each smoothie. What percentage of a quart will be left after I've made the smoothies? So before we start, the variables that we'll be using would be the B on the left, which represents 1 quart of almond milk, which equals 4 cups of almond milk. And the A variables will equal 1 cup of almond milk each. So our question to find the percent would be, given A and B, what percent P of B is A? Our answer will be 1 cup is 25% of 1 quart. To find the part, our question will be, given a percent P in the whole B, what is A if it is P percent of B? Our answer for that would be 1 cup is 1/4 part of a quart. To find the whole, our question would be, given a part A that is P percent of the whole B, what is the whole B? Our answer for that one would be 1 quart is 4 cups, which is 100%. So to answer my question, what percent of a quart will be left after I've made the smoothies? My answer is 4 cups equal 1 quart. 1 cup times 3 smoothies equal 3 cups. 3 cups is 3/4 part of 1 quart, and 3/4 is 75% of 1 quart. Therefore, there will be 25% or 1/4 part or 1 cup of almond milk left. Well, that is all I have. Thank you. It's been a great semester. I hope you've learned something. I hope you soaked in all the information and retained it, and hopefully you can use it in the future. I know I've had fun making this PowerPoint, and I hope to see you soon. Bye.